So here's a road dot, and I found it, and I thought, well, I wonder if this is related to Platonic solids. And the reason I thought that is that if you make a dodecahedron, and then you add this onto there, you get a sphere. And you can see here, I've got all 5 Platonic solids with the appropriate road dot, if you can make it there. These things were invented in 1961 by Dr. Botts in California, and I was wondering if he knew what he was doing, as in this was a slice off a sphere, leaving a dodecahedron, or if it was just random. And I measured this, and it certainly fits exactly onto a dodecahedron to make a sphere.
Oh.
And so if you go back two slides, that's the model.
Next one.
Previous one. Go previous. Can you go previous?
On the bottom there.
Yeah, the road dot.
Oh.
This one shows the road dots as they would appear from each of the Platonic solids, and the dodecahedron is the 4th one up, and then and there's a highway to this way.
What's that made out of?
I would say polycarbonate or something.
Oh,
I'll pass it around. It's a real road dot. I just found it in the street.
Oh. I mean, it's really for use on a road.
These are the dots down the road. That
Yeah,
you've got.
I mean-
It's still got the tar on it.
Oh,
Yeah.
oh, it's actually, oh.
Yeah.
I thought that was a design.
If you go back to the previous picture,
Go back.
yeah, as in
So they made
This
it
one here?
exactly
previous.
the 12th of a dodecahedron.
No, yeah, so
The next one.
from before. Yeah.
Oh, we're going backwards. Okay.
Yeah. There you go. And so there's my dodecahedron with 12 of these road dots stuck onto it, and you can see that it recreates the sphere. And I do have a picture of another road dot that's actually very tall and round very, very big and yellow instead of white, and I've calculated that is as if it's been sliced off a tetrahedron, you know, as in you slice off the dots and what's left is a tetrahedron, and of course it's a much bigger thing. The reason I did this partly was because this is a nice example where you can actually examine road dots and compare them to the 5 Platonic solids. And Richard had a question some years back about how to make you end up making a tetrahedron, and you wanted to find the center of the sphere, you know, all 4 points around the sphere. And I was saying the Platonic solids data is online all over the place. There are tables, and so you can for instance, easily calculate all the math by just using those tables of equations of Platonic solids.
Next.
Yeah, so let's see what else we've got. Okay.
This one.
Yes, you can. Yes, let's look at that one.
Oh, that's an image.
Oh.
That was what I had in my hand. I get on the way here, and they didn't seem to mind. Even though there's two box cutters and long pointy objects, scissors, and bits of wire and that kind of stuff. Yeah. And it's an example of just I'm always sort of testing things. So yes, I need a glass of water.
Get a bottle down here.
And so, switching gears completely. Oh, if anybody wants all the math and stuff, all the road dot stuff, I've sort of 90% written up a paper, and I'll just sort of send it to you at some point. And the same is true of this note I've got now. So some years ago, I was playing on the computer, and excellent. And I did an averaging experiment where I was generating random numbers, and if you generate just an ending stream of random numbers from 0 to 1, you would expect their average to be a half. And what I found was that it wasn't a half. I can't remember what it was now, but it's something like a third or something. Or maybe it was a half, and I did some other experiments where I expected the average to be, you know, just add total and divide by n, and you get a number. And I got things that were very unexpected. And so I with the help of numerous friends, figured out ways to see what was going on, and I kind of rediscovered the binomial theorem and all kinds of stuff. Yes, I sent Joe Horn an email, and I said to him, "Hi Joe, I have a random maths answer, and I'm wondering if you can help me find the question. The answer is about a half." And Joe actually replied with a very, very good email. He said, he explained the area under a curve, the calculus of the area under a curve, and what it all means, and because I was basically averaging a bunch of numbers, and so the ultimate question was, how long is a line? And the way I was doing that was to say, you get a 1 unit square, and you pick 2 random points in it, and then you just measure the distance. And basically, since I was adding random numbers and then collecting about 1 million of them, and then dividing down by say 4, or by 1 million, I was hoping to get sort of random points in this square. But the averaging that I was doing didn't give me my expected numbers. It gave these very strange numbers, and so I was trying to find the meaning of or how that the method would explain those results. And years have passed, and I actually found the answer, and the answer is a quadruple integral, but essentially it's what's called a line picker. And I'll let you go to say all from website where they've got a good description of what the line picker is and the math behind it, but it does give you sort of the length of a random line, and that's quite interesting. Okay.
Next slide.
Oh, let's see.
This one here.
I think we're yeah, it'll be fine. Well, let's see. I think yeah. Why don't you go to the first slide?
Go back to the first.
You should go back to the menu, as it were.
This one here?
The first slide on yeah.
Up here.
Yeah. So this is where this came from. The 5 Platonic solids are all here. Oh. There's the tetrahedron, cube, octahedron, dodecahedron, icosahedron, and in the first case, the tetrahedron and the cube have 3 bands around them, and then the 3 bands have been taken out at the bottom and exist on their own. In the second column, there's a cube and octahedron, and they have 4 bands around them. And the bands go from the center point of the edge to the center point of the edge. And in the case of the solids of the triangle, there's only one solution. But in the case of the square, there are 2 solutions. And in the case of the pentagon, there are 3 solutions. Also 2 solutions. The third column shows a dodecahedron and icosahedron, and at the bottom there's a six-banded object that appears, and you can see that the icosahedron has those six bands drawn on the surface, and that was actually the basis of a global grid method used by a geoscience professor developing global grid. And we were chatting one day, and I said, I think there's more than just a six-banded object. And so I went to the dodecahedron, which is the last column, and I found that the pentagon had two possibilities. It can go from the midpoint of the edge to the midpoint of the adjacent edge, or to the opposite edge. And that's where this came from. And to me this is very beautiful. It's also very rare. I've seen these. The only place I've actually seen these is the turmeric ball, which is a Japanese ritual gift, and this design is in some of those things. And to me that's kind of significant. The six-banded object, at the bottom of the third column, that is the same design as the takraw, which is in Thailand, the kickball, and it's woven out of rattan vines. And so those two objects only occur in those places there. You don't see them anywhere else. And that to me is kind of interesting. But with these things I made tiny and the size of 8-foot sphere with the kids to play in.
Next.
Let's see. Okay. I've got a. Oh, as long as this still works.
Yeah.
There we go. I'll stick it here. What was I going to do next? Let's see. Oh yes, and the next picture, if you should just show that.
This one here?
Yeah. That thing is exactly the same as this. It's just made with ribbons. It's inside a glass ball. So yeah, that was kind of cute.
It's glass, made out of glass?
It's a glass, hollow glass light bulb, and then ribbons inside it. Yeah. Oh yes. Now again, changing subjects completely. Something I've done recently is explore factor diagrams. Factor diagrams, I suppose I should have a picture. Is basically a way of drawing numbers using just dots. And here's a picture right here. And it shows 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But 1, 2, 3 is just 1, 2, and 3 dots. 4 is 4 dots, but it's in two groups of 2 because 2 is a factor of 4. And 5 is prime, and so 5 is just 5 dots in a circle. And then 6 is 2 by 3 or 3 by 2, and so on. And I basically just somebody invented that system, and I've been playing with it, and I made just a huge ton of graphics, and I brought them here. I brought some samples. Here we are. Very colourful. These ones, as you can see, there's 1, 2, 3, 4, 5, 6, 7. This is in Ulam spiral configuration, just for the fun of it. This one is in a phyllotaxis spiral, like the in a sunflower seed head. You get those spirals. This is the centre of one of those. But anyway, it's an interesting concept, I've got innumerable variations, and it's possible that this may be like an alternative or a complementary method of looking at factors. In this picture here, it's in the spiral format, and factors can actually form subspirals, and so all the factors of 3 or 5 or 7 form some of these radial spirals coming out. So it's a very interesting way of exploring factors and other things graphically, and so I've made these posters, and this is my first product on my webpage that I'm actually going to start selling.
So the dots are colored according to how how the numbers are factored
Yes,
or something?
yes. So on the top is a key, and so the red is 2s. The purple,
Means
the
it has
blues-
a factor of 2 or
Yes. So the red. Well, let's see.
and 3.
This is 5, the cyan one, and then you can see there's a 5 here and a 5 here, and there's cyan.
So would 10 be red or green? Would be the 2 or the 5 count?
Good question. And because of course
It's got both.
a number that has 2 factors has 2 representations.
Yeah.
3 by 2 or 2 by 3, and a number like 24 has 4 different
Yeah,
representations.
right.
And so there's actually 24 possibilities.
Mhm.
And so you arbitrarily choose. I've got versions that show the lowest factor and versions show the highest factor.
Oh.
And then some that are just arbitrary.
Oh.
They're still consistent, and this is the key, and this is just the prime numbers.
Oh, yeah.
Yeah. So
You've got a special color for each prime number. Yeah.
well, I do, but I mean, on what's become the standard set, it's fairly consistent. But you can change them at will.
Hmm.
But they're consistent within any picture. And so I was wondering, these I sell on the webpage for $10, but my inclination is I'm sure I've got enough for each person to take one home, and because I want to sell it to you, or maybe you can make a donation. I don't know what to do. So anyway, I think there's interest. Look at these and make me an offer or something. I've got 2 things that I've made just to show off since I'm here, and this thing here. This is made of 16 half cubes drawn together as a piece of string, but it has very interesting properties. And when Jim was talking about liquid helium and stuff, I call this the super cool liquid cube, and it's very malleable and flexible, and like a it's an unremoved cube because it solves itself. There's a cube, and then you can make other shapes out of it, and it kind of just pats into shape.
Huh.
So it has interesting properties.
Are they fastened with string, you say?
Yeah, there's a piece of string in the middle,
Oh.
and the
What is
key
it? String or rubber band?
string.
Oh, kind of like strung like beads or something?
Yeah,
Or-
yeah.
Oh.
Just in the middle, and there you have a. I'll pass this around so you can play with it. The section of the cube is what's interesting. I mean, there's infinite ways you can take the cube, but this goes through all 3 axes, so it makes each one a universal joint. And I've seen robots built using this dissection. And so as one around the other, you get X, Y, and Z all represented, and that's why I think it has the properties it does. And then this thing is the I've been sitting on it for a year or 2. It's also a cube. This is a cubic dissection,
Oh.
and there are 32 pieces that it dissects into, and this is the another version of the box. And when I show you the insides of it, you might guess what this is. There's the insides of the box, and this is indeed a chess set. So you might all be interested to look at that. And they're all interlocking parts, and the king and the queen used a lot by their heads, and the cubic dissection here is exactly the same as the thing that's going around. It goes to all three corners as well. Yeah. Let's see. I think I'm done. Oh, and just for the hell of it, I'm reading this right now. This is the Book of Awesome. It's actually called The Nature of Computation, but it's a great bedtime reading.
Thank you.
The king and queen, are these intended to be chess pieces then, or the?
Yes, this is a chess set.
It's a chess, I see it.
Yes,
yeah.
yeah, the whole thing is a chess set. Pawns, queens, kings. And my joke is that the king and queen can exchange places, and bishops go both ways.
Oh, yeah. Yeah, I know. Yeah. It's pretty neat.
Okay, well, thank you
Oh,
very
I
much.
see, and the
Jeremy.
chessboard is on the inside.